Well, I'd like to thank Professor Jong-Soo Kim for the invitation and Dan's friend for the introduction. So I'd like to first give a brief introduction to invariant metrics. So when you say a metric, we mean the length of a vector in Cn. So let's say if this is a domain in Cn, say if P is a point here. By the way, can you hear me? Am I loud enough? And if C is a vector in Cn, then we define the metric of C, and we give the length of this C, and let's say Fk. Defines the length of the metric, and by integrating this length over a curve, we can calculate the length of the curve, and so on. So we say F is invariant. F is an invariant metric if it is invariant under biholomorphic mappings. So let's say if F is invariant under biholomorphic mappings, so let's say if domain omega 1 is here and we have a biholomorphic mapping phi, and another domain omega 2, say phi is biholomorphism, and say if point P is here and C is here, then if F is invariant under phi, then we should have F omega 1 at peak C must be equal to F on the domain omega 2 at phi P. Say here's phi P and phi star at P of C. Then we say the metric is invariant. So what is the invariant metric on the unit disk in C? On the unit disk in C, well, we have very few kinds, only two kinds of, biholomorphic mappings, Möbius transform or rotations. So if this is a disk, say 0, and say if here's a point Z, and say, let's say, if you have a vector C here, then if it is invariant, then Fzc must be equal to, say, Möbius transformation, say, well, let's say it is P. Möbius transformation 1 minus P bar Z, Z minus P. And since that sends P to 0, it must be equal to F at, say, this is phi F0, and then phi prime at P of C. So let's say F0 of some vector, say V, is modulus V. Then this must be, this F, the metric at the point P, the direction C must be equal to just phi prime P of C. And this is easy to calculate if you differentiate. Oh, I think I broke the microphone. The clip is gone. Oh. Can I just proceed without. And then if you differentiate, phi, if you differentiate tau, it's 0. If you don't differentiate tau, it's 0. So you differentiate tau, and then you get 1 modulus c over 1 minus p squared. Yes. 네? 아. 힘든데. And this is the Poincare metric, the famous Poincare metric. So Poincare metric is defined this way, and any invariant metric on the unit disk must be a constant multiple of Poincare metric. So, but then this metric is defined only on the unit disk. So can we, is there an invariant metric that one can use on any arbitrary domains in Cn? That's the Kobayashi metric generalization of Poincare metric. Well, there are several generalizations, and one of them is the Kobayashi metric. The Kobayashi metric. It is defined in the following way. Let's say omega is a domain in Cn, P is again a point inside the domain, and Xi is a vector in Cn. Then I put the subscript k for Kobayashi. Fk p Xi is defined as 1 over supremum of alpha, where there exists a holomorphic mapping from the unit disk to the domain, holomorphic. And phi 0, it maps 0 to the point P. And then phi prime 0 is alpha times Xi. And alpha is positive. So if you stare at this definition, it is defined in such a way that you measure the maximum, the largest possible complex one-dimensional disk in the direction Xi, say something like this, and then you choose the maximum sort of radius in the Xi direction and take the inverse. Then that gives you the Kobayashi metric. So we are taking the inverse. So as the point approaches the boundary, there are less and less room for any disks to fit in. So alpha goes to 0 if it is round. And so the metric goes to, it blows up. Okay. So, well, this Kobayashi metric on the unit disk is equal to the Poincare metric, is equal to the Poincare metric, or say modulus Xi over minus p squared. And we can show this by only checking it at the origin. So 0 Xi, is it really the length of the Xi? Well, yes, it is by obvious reasons. So let's say phi is a mapping from the unit disk to unit disk that sends 0 to 0 because we are measuring the metric at 0. Then and say phi prime 0 is alpha times xi. Let's say alpha is positive number. And we are in C1, so xi must be some complex number. Then by the Schwarz lemma, we have alpha xi is less than or equal to 1. So length of alpha is positive number, so alpha must be less than 1 over modulus xi. So this is the upper bound for alpha, but then, this is, if you take phi as xi over modulus xi over z, then this is one of such mappings phi. So we get the supremum of alpha is actually 1 over modulus xi. So if you take the inverse, then you get this, right? And so it is equivalent to Poincare metric on the unit disk. And is it biomorphically invariant? Is Fk pxc invariant? Under biomorphic mappings? Well, yes, because say if you have a domain omega 1 and another domain omega 2, and say phi is some, not necessarily by holomorphic mappings, but some holomorphic mapping. Say phi is holomorphic. Say p is here, and phi p is over here. Then we are taking the maximum possible alphas and then take the inverse. So if the candidates for such alphas comes from the mappings from the unit disk that sends 0 to here. But then the candidates for the metric here includes the candidates for these guys, because you can take the composition. So if you take the composition, then these are also candidates for the metric on omega 2. So this domain has, more choices of mappings. So hence the supremum must be larger. So we can say, and we are taking the inverse. So if the supremum is larger, then the metric is smaller. So we show that Fk on omega 1 at peak C is greater than Fk omega 2 phi p phi star p c. And if phi is by holomorphic mapping, then you have inequality in the other direction. So hence it is biomorphically invariant.
So when you say invariant metric, it is not necessary to take omega 2 is same as omega 1?
Oh, no, not necessarily. It can be any
So the range may not be equal to domain. It is also okay?
Hmm?
So you are taking omega 2,
Yes.
which may be different from omega 1.
Right, this omega 2 can be in different dimensions.
But you are talking about invariant matrix. So
Yes.
what I'm saying is maybe domain should be same as range.
Well, if phi is biholomorphic, then it should be. But if it's just holomorphic mappings, then this inequality is just fine. But when we say it is invariant when when we have equality when phi is a biholomorphic mapping. So we have inequality for holomorphic mappings. If it's a biholomorphic mapping, we have inequality in both directions. Hence, we have equality. Yes. And another invariant metric that I'd like to introduce is the Kerr-Theodor metric. So if you, again, same setting, P inside the domain, and C some vector, then the Carey theory metric, let's say C for Carey theory, PC is defined as the supremum of, say, summation df dz1, well, c1, say omega is in Cn, j's, where f is holomorphic mapping from the domain omega to a unit disk. So the direction is the other way. Kobayashi metric, you look at the image of the unit disk here, you consider bounded holomorphic functions such that fp is 0. And this is the Carey theory metric. And this Carey theory metric satisfies the same property as the Kobayashi metric. It decreases under holomorphic mappings, and hence it is invariant under biholomorphic mappings. And it is equal to the Poincare metric on the unit disk. So, and the Kobayashi metric, well, looks at the image of the unit disk in C in the domain omega. 0 goes to P. And then the Carey theory metric considers the bounded holomorphic functions from the omega to the unit disk. That sends P to 0. So if you compose these two, phi and f, then it's a mapping from the unit disk to unit disk. And by Schwartz lemma, you can easily show that fc at peak C is less than fk is less than the Kobayashi metric by Schwartz lemma. Yes?
Is this metric actually continuous or smooth?
Carey theory metric is continuous, but Kobayashi metric is not.
Oh.
Well, I mean, it is continuous. I mean, under certain circumstances. I mean, with extra hypothesis, complete. Yeah. So, the question we want to ask is, on which domain are these metrics complete? So this defines the length of the vector. So fk, pick C, defines the length of the vector. And if you have a curve in Cn, then you can calculate the distance of this curve, I mean the length of this curve, say gamma, by calculating, the tangent vector of this curve along this, by integrating this length of the tangent vector with the Kobayashi metric along this curve. And that gives you the length of the curve, and you can define the distance between 2 points as by taking the infimum, say, length of curves, gamma. Gamma connects P and Q. So you can define the distance between 2 points using this definition. And we say a domain omega is complete with respect to the Kobayashi metric, say. If any Cauchy sequence with respect to this distance is convergent inside the domain. If any Cauchy sequence with respect to Kobayashi distance converges inside the domain omega. So, well, if you look at a unit disk in C, say 0, delta, then the Poincare metric then this unit disk is complete with respect to the Poincare metric. Well, you know, we have explicit formula for the Poincare metric, and it is easy to calculate the geodesics. For Poincare metric, it's actually a line or circles. And then, you know, the distance, if you integrate the Poincare metric along such geodesics, it's always infinity if you integrate it toward the boundary. So, and then here, if you look at the definition of the Poincare metric, say 1 minus z squared, Poincare metric at the point z, c, then when z is, say, 1 minus delta, say z is very close to the boundary, then this becomes, well, if you subtract, you get 2 delta minus delta squared. So this is approximately 1 over delta. So if you calculate 1 over x from 0 to something, then it's infinity. So then what about the domains in Cn? Well, if you look at an annulus, say modulus z between 1 and 2, well, I mean, this z is a multiple, z1, z2, say in C2, then as the point approaches the boundary, say this is, say, 1 plus delta, comma 0 or something. Say p delta is 1 plus delta, comma 0. Then the Kobayashi metric at this p delta in the direction, normal direction, say 1, 0, is not 1 over distance. It is 1 over distance to the 3/4 power. And this is by Krantz. So, obviously, if you integrate 1 over x to the 3/4, then it is finite, not infinite. But it still blows up. But I mean, this domain is not complete with respect to the Kobayashi metric. Not complete. Well, then what's the then on which domain are these metrics complete? Well, this domain is not a domain of holomorphy. So the question is, if omega is a domain. Well, I explain what this means shortly. Domain of holomorphy. Then is omega complete with respect to invariant metrics, let's say, any invariant metrics. So what is the domain of holomorphy? We say omega is a domain of holomorphy if at each boundary point, at each boundary, you can find a small neighborhood U, so and some holomorphic function. There is this U and there is this F holomorphic on omega, such that there does not exist an extension of F holomorphic on omega union U and equal to F on omega. So at each point, if the function, you can find a function that doesn't extend across, then that's the domain of holomorphy. And if you look at this domain is not a domain of holomorphy. Any F holomorphic on, let's say this is annulus, say A, on A extends across the inner boundary and extends actually to the whole disk. And then Zephran will explain why this is true in his talk, which follows my talk. Okay. So
So that is also true for dimension 1, please?
Oh, that's a very good question. In dimension 1, any domain is a domain of holomorphy.
I will do that as well.
Yes. So how can, is there any geometric characterization for such domains of holomorphy in Cn? Yes, there is one. So let's say if omega has C2 boundary, and say omega is defined as a sublevel set of some real valued function, then, this is called defining function. Then we say omega is pseudo-convex if summation of, say, in Cn when you take the complex Hessian, in the complex tangential directions, then this must be greater than 0. So here this C is in the complex tangent space of the boundary, and P is a boundary point, any boundary point. So this must be true for all P and for all C. Oh yes, here. Then it is called pseudo-convex. And if it's pseudo-convex, it is equivalent to domain being a domain of holomorphy. Well, how is it different from convexity? Well, omega is convex if we use the same notations. If summation as rho xj xk p and say vj vk, and here jk goes from 1 to 2n. So omega is Cn, so it's in real 2n dimensions. And say x1 through x2n are the real coordinates, and v is in the tangent space, Tp. Then it is. Then we call it convex. And it is equivalent to the well-known definition of having, if you have a line segment, 2 points, then if you connect them, the line segment, the whole line segment should be in the domain. Yes, you have a question?
This is positive.
Oh, yes. Thank you. So same for all p. For all p on the boundary, and for all v. So, is convex domain pseudo-convex? Yes. So if it's convex, then it is pseudo-convex. And are there any examples of pseudo-convex domains that are not convex? Yes. So if you look at any real one-dimensional curve in Cn, say real one-dimensional curve, say in Cn, and if you fatten this curve a little bit, like this, fatten it a little bit, then this is pseudo-convex. Then it is pseudo-convex. But it is not necessarily convex. So if you look at this domain, the defining function of the outer boundary is defined as mod z1, let's say z1 squared plus mod z2 squared less than 2. So let's say minus 2 less than 0. When you take the complex Hessian, it is obviously positive. But if you look at the inner boundary, then the local defining function of the inner boundary is actually it is the other direction. So you get x minus plus is less than 0. So this becomes your defining function, and the sign is switched, so you have negative complex Hessian. So it is not pseudo-convex at every point, everywhere, and so it extends across the boundary. Okay. So what do we know about the behavior of invariant metrics on pseudo-convex domains? By the way, here I add one more definition. We say omega is strongly pseudo-convex if we have strict inequality. If this is strict, then this is strict. Then we say it is strictly pseudo-convex. So this is a theorem of Graham. If omega is C2 boundary, strictly pseudo-convex, then as a point approaches the boundary, say the point is P delta, where the distance to the boundary is delta, and say this is the normal direction, and then say this is tangential direction, C. So its nu is real normal direction on some boundary point P, and let's say at some boundary P, and say P delta is P minus delta nu. Outward normal direction, and say C is in the complex tangential space at the point P. So let's say this is point P. Then the Kobayashi metric P delta C nu blows up at a rate of 1 over distance to the boundary. And the metric in the tangential direction blows up at a rate of 1 over square root delta.
I'm sorry, I'm just confused. So
Yes.
when you say that tangent vector,
Yes.
you mean the complexified tangent vectors? Probably they should be the right one, but
Well, if you have
the boundary omega is as a real way for the ultimate engine.
right. So here, when we say complex tangential vector, if you have a domain omega, say omega is in Cn, then the real tangent space has 2n dimensions. And if you take one real normal direction, and there's another normal direction, another complex normal direction when you take I times nu, and that's complex normal direction. And then so we use 2 dimensions for these 2, and then the other the other 2n minus 2 dimensions, the vectors there are, it is closed under multiplication by I. So that's the complex tangent space that I'm talking about.
Which is actually complexified, actually.
Yeah. Yeah.
No. It's a subspace. Yeah, subspace of these complex
n minus 1.
Yeah, so that should be actually complexified. It's a subboundary actually. Otherwise, it's a boundary omega. It's a real manifold, so
You don't need to complexify.
It's not complexified.
I still don't then understand what.
It's all embedded in Cn, so we don't need to complexify actually.
Okay. It's a subspace of C vector subspace.
Well, if you use almost complex vector J, that's J invariant. That's real subspace.
I'm going to see clarification.
Well, let's say the domain is a half space. Say omega is real z2 less than 0. Then this 0, 1 vector. If you take this is the real normal vector. Real one-dimensional vector, and then 0i is another vector, but that's still real tangents. Well, if you say, let's say 0, 1 or something, 0, 0. Well, but it is 0i, and then and the complex tangent vector space for this domain is So t, say 0, say 0, c, boundary, omega is just, you know, all the points that, I mean, the vectors with 0 for the last. Yes, yes, yes. So, okay, so Kobayashi metric blows up at a rate of 1 over distance to the boundary. And the tangential directions, it is 1 over square root delta. And it is actually because if you look at a ball like this, then if you look at a point close to the boundary, then if distance is delta, then this distance is about square root of delta. So that's basically why it is. You have more room in the tangential directions than in the normal directions. So, but this is only for strong-ish convex domain. And then, you know, these strong-ish convex domains are complete with respect to the Kobayashi metric. And let's see. But it is strong-ish convex. So that means if the domain is given like mod z2 squared, mod z, let's say z1 squared mod z2 to the fourth less than 1 on ellipse, then the point 1, 0, then this domain, the boundary of this domain is not strong-ish convex at 1, 0. So this doesn't apply to this ellipse. So it is my theorem that if omega is convex and smoothly bounded, then under the same setting, say p delta, delta, so here's p and this is the nu, and C is complex tangential direction. Then the metric Fk at p delta in the normal direction again blows up like 1 over distance, and then Fk p delta c is blows up at a rate of 1 over delta to the 1 over m, and this m is the maximum tangency of the boundary in the direction of c. So m is the supremum of, say, omega is defined as rho less than 0, supremum of rho of phi, the vanishing order at the point P, where phi is a disk, is a mapping. This is one-dimensional curve, and phi 0 is P, and phi prime 0 is some complex number times C. So if it's an ellipse, then if it's an ellipse, then we have Fk, P delta nu is just 1 over delta. If omega is say Z1 mod Z1 squared plus mod Z2 to the fourth less than 1. Well, let's pick a point.
Why do you call that an ellipse?
Excuse me?
Why do you call that an ellipse?
Oh, ellipsoid.
Yeah, but is it ellipsoid?
This one?
Yeah. Of course. So, looks like, but it's.
Well, general ellipsoid.
Yes, but
Yeah.
degrees.
Yeah, yeah. General, I mean, analytic ellipsoid.
Pseudo ellipsoid.
Yeah.
Wait. Okay.
Yeah. So let's say this is a point 1, 0. Say this is your point. And say Z2 direction. Say this is the Z2 direction, 0, 1. And then say this is 1. The P delta is, say, P delta is, say, 1 minus delta comma 0. Then what this means is the Fk at this P delta in the direction 1, 0 is about 1 over distance, and Fk, P delta, in the direction 0, 1 is about 1 over delta to the 1/4. And these convex domains are also complete with respect to the Kobayashi metric or character metric. But if omega is, say, general pseudo-convex domain, say weakly, pseudo-convex domain in Cn, say smoothly bounded, then we actually don't know how it behaves near the boundary.
So
It is open.
So this is actually complete, right?
On convex domains and strong pseudo-convex domains.
Sorry, say again.
On
Strong-
convex domains or strong pseudo-convex domains.
In your case, it's complete, right?
Oh, yeah. I mean, every convex domain is complete.
Okay.
Yes. Well, but I mean, the completeness doesn't come from these estimates. Actually, it comes from, I mean, if you have a convex domain and you can map it to the unit disk, and then for any boundary point, you can map it to, you can find the mapping that sends this boundary point to the boundary of the unit disk. And as you know, the metric, this Kobayashi metric decreases on the homomorphic mappings. It is complete here, and the metric is greater here, so it must be complete here. So that's why it is complete. And this metric estimates, I mean, gives more, I mean, convincing, it is reasonable to expect this behavior. And so we don't know, actually, the answer to this one. So is any weakly pseudo-convex domains complete with respect to invariant metrics? We don't know. It's still open. Well, we partially know. I mean, for example, if omega is weakly pseudo-convex.
When you say weakly pseudo-convex, you mean pseudo-convex?
Well, yeah, and there's at least one point where it is not strongly pseudo-convex. Right. Excludes strongly pseudo-convex.
You exclude it.
Yeah. So there is at least one point where it's bad. You have at least one bad boundary point. So if omega is weakly pseudo-convex in C2, then it is complete. We know this. And any C1 bounded pseudo-convex domain, I mean weakly or strongly, is complete with respect to the Bergman metric, well, which I haven't defined yet. So
Before you raise, I came late. So what do you omega is set of low is less than 0? Or what is that? Greater than or equal to 0.
less than 0.
Which, so the one you raised just now? Rho. What is rho?
Rho is a defining function. So if if omega is a ball like this, then your rho is mass z1 squared. Yeah. Yes. Yes. So the Bergman metric is another invariant metric, and it is defined as so say B P C is defined as summation JK log K ZZ ZJ partial ZK bar CJ CK bar, and you take the square root, where K is the Bergman kernel, K Z zeta is the Bergman kernel. So that means if F is holomorphic and L2 in omega, inside the L2 omega, then F at Z is, this K reproduces the L2 holomorphic functions, the integral on the omega volume integral, and F zeta, and K Z zeta d volume zeta. So if you define the invariant metric this way, Bergman metric, then any pseudo-convex domain is complete with respect to this metric.
So what's the relation between Bergman metric and your other two metrics?
Yeah, that's a very good question. I'll talk about that, later, maybe 5 minutes later. Yes. So how many minutes do I have? 15 minutes? 5 minutes? Okay, I'll be quick. So if the domain, we want to show that if omega is pseudo-convex, weakly pseudo-convex in Cn, then it is complete with respect to Kobayashi metric. And this question is still open. And one would expect that if you estimate the metric near the boundary, it should behave something like this to have the completeness, like in the other domains. But then it turns out it's not actually the case. So the example by Fornes and myself. So there exists a domain in C3, bounded domain, smoothly bounded, and it is weakly pseudo-convex. Pseudo-convex, such that one can find a sequence of points that goes to that converges to a boundary point, say P, say this point is Pn. So Pn goes to P as n goes to infinity. And say delta n is the distance from Pn to the boundary point. And say all these points lie on the real normal line. at the boundary. Well, it doesn't look like real normal line, but let's say it's real normal line. Then then there exists these sequences. There exists these sequences such that the Kobayashi metric at these points in the direction, the normal direction, nu is less than 1 over an delta n. And so 1 over delta n is the distance to the boundary, and this an goes to infinity. So on this domain, the metric obviously doesn't blow up as 1 over distance as the point goes toward the boundary. So, but this doesn't necessarily imply that domain is not complete with respect to the Kobayashi metric, because these are only this is specific sequence. One sequence. So it doesn't necessarily. On the other points on the real line, it might behave like 1 over distance, but it doesn't behave like 1 over distance. Uniform way. So, yeah. So this question is still open, and it's always in my head too.
Even for this domain, you have.
We don't know whether it's complete or not. Yes. And about your question, the relationship between the metrics. So the Kobayashi metric, we know the Kobayashi metric is greater than or equal to the character theory. This is by Schwarz lemma. And the Bergman metric is greater than character theory. This is a theorem by Kyung-taek Han. It's actually a very simple argument. And between these two, one would expect that Kobayashi is greater than the Bergman, but Bergman is greater than Kobayashi. On some domains, and it is less than Kobayashi on some other domains. So there is no uniform inequality between these two. So it's not comparable. So these two metrics are not comparable. Yes. Any questions? Any other questions? I'm sure Dan will fill in some of the details. Well, no, just the extension part.
You done?
Huh? If you don't have any other questions, then well, then that's
Other questions?